Good evening to all. Hello, welcome to this 23rd session of Experimental Methods in Thermal Engineering. So, in the last lecture, we had discussed particularly about the particle image velocimetry. In this particular lecture, I will conclude our discussion on the measurement of velocity and its companions. And in particular, we will over here try to see some of the measurement techniques which are based on uh, density based flow visualization. Okay, so over here basically what these techniques are, these are also based on the optical visualization. Moreover, while we are visualizing the flow phenomenon, that actually is based on the difference of density of the fluid. Okay, so the major idea is that while we will be having variation of the density inside the flow field, based on that we will try to identify the flow structures. Okay, and apart from that, in this particular lecture, we will also see some of the techniques based on positive displacement based measurements. Then we will also try to see Coriolis mass flow meter, and then at the end we will try to see that what are the different arrangements for using the pitot tube based velocity measurement. Okay. So I will start my discussion first with the density based flow visualization techniques. So the general idea over here is that density is having direct dependence on refractive index. So this N over here is nothing but our refractive index of the fluid medium. So based on this Gladstone Dell equation, you can see that refractive index is related directly to the density field. We are having N minus 1 equal to K times rho, where this K is some parameter which is nothing but having dimensions as that of 1 by density. Okay, 1 by rho. Uh, Now, this particular constant is something which is known as Gladstone-Dell constant, and this equation is valid only for gaseous medium. Okay, so this particular equation is actually valid only for the gaseous medium. So while we will be talking about flow visualization, majority of the time, based on this density stratification, we will try to actually visualize only the flow configuration where gaseous medium is our participating fluid. Okay, generally what we do, if we are having liquid as our participating medium, in that case it becomes very easy just to add some dye, fluorescent dye into the liquid medium, and we will be able to visualize the corresponding flow field based on the traces of that dye. Okay, however, in case of gaseous, that will not be very effective. So what we do, we employ the principle of change of refractive index of the medium in proportion to change in density of the medium, and based on that we try to visualize. So in the Z direction, we are actually placing some test object, and if we consider that within this test object, we are having change in refractive index of the fluid medium which is there inside this particular test object. So what will be happening if we are incidenting a light ray? That light ray will be actually refracting or changing its angle, and finally we will be having some deflection in its path. Okay, so over here you can see that our light ray is basically moving along the z direction. So obviously if we are having any change of refractive index in the z direction, that will not cause the deflection of the light wave. The only deflection which will be caused in the incident light ray, that will be because of the change of refractive index in y direction and change of refractive index in x direction. So that is something which we know from our basic optics, that while a ray of light is actually passing through a medium, there should be change in refractive index in the normal direction. Then only we will be having the deflection. Okay. So what we are considering, because our ray was actually passing along the z-axis. So obviously, if we are having the change of refractive index in y direction as well as in x direction, that will be leading to the deflection. So you can see over here, in y direction, the angle of deflection is epsilon y, and in x direction, the angle of deflection is something which is given as epsilon x. Okay, and you can see this was the actually original point where your direct ray without any deflection could have reached, and in actual practice it has actually gone to some point q dash on the recording plane. Okay, so you can see we are having some displacement delta x in the x direction and displacement delta y in the y direction. Okay, so the main idea is that while we will be having the deflection in the ray, so the very first parameter is either we can measure the change of deflection. So first parameter is deflection, which we can measure. Second parameter is directly we can measure the angle of deflection. Okay, and third parameter, which will be coming nothing from the wave nature of the propagation. So that will be something we may have nothing but phase shift in between the two waves. Okay, so these are the three basic principles based on which we will be actually try to visualize the flow field. So let us now try to see the general idea of density measurement. So what we will be having some light source. Okay, so this is nothing but my light source. Now this light source will be emitting light rays, and then we will be considering some lens, and that lens will be actually directing all the light rays in some particular direction. Okay, after that we may have now different type of arrangement. So one of the arrangement, as just I was telling you, that we may have our light ray which is actually incident on some medium. Okay, so for example, this is our test medium, and what will be happening now, I may consider that this as my x direction and this particular direction as my y direction. So if I say that along the direction of y, we are having actually constant density. It means I have a patch over here which is having nothing but constant density rho1. Then if I consider another patch which is having constant density rho2. Then if I consider another third patch which is having constant density rho3. So over here you can see that we are having nothing but increase or decrease of the density only along the x direction. So in case our direction of the incident beam and the direction of the change of density, or which is directly related to change of refractive index, if both are same, we will not be having any deflection in the path of the light wave. Okay, so this light will be actually moving along the direction of its incidence. Okay, rather if we consider another situation that our light ray is coming like this, and instead of having the variation of density in x direction, if we consider the gradient of density in y direction. Okay, so now what I am saying, that this is my test section, and along this entire section everywhere if I have the gradient of density along the y direction. So in this particular direction now, if I have gradient. Okay, so what I have nothing but the gradient of density field. It means I have del rho by del y. So now what will be happening, if my light wave is actually coming in this particular direction, so this light wave will actually try to deflect towards the higher refractive index. Okay, so over here what will be happening, we will be having the motion of the light wave along this particular curved path. Okay, so over here you can see this was nothing but the incident direction of the wave, and this is the final motion of the wave. Okay, so in this particular region we were having a gradient, so because of that actually light wave has tried to shift it towards the higher value of the refractive index, and where after that when we have reached to the surrounding medium, in this particular surrounding medium now we will be having some fixed value of the refractive index. So because of that, the angle at which light wave has come out of this plane, actually it will be moving in a same direction then. Okay, and particularly whatever the angle we are getting over here, let us call that angle as nothing but some epsilon angle. Okay, so now it means one of the important criteria we are having, that we should have the gradient of refractive index, or in other words I should say the gradient of density field in a direction normal to the direction of the incident field. Okay, so if we are having the gradient in the same direction, then we will not be having the deflection of the light wave. Okay, so this is the actually basic idea. So now we can consider one situation, that in my test section I have say only the gradient of density in this particular zone, and after that also I have sufficient amount of fluid medium inside this test section, but here in this particular zone I don't have any gradient of density. Okay, so in that case what will be happening, while the light ray will be coming, it will be only deflecting in this particular zone. So in this particular zone it will be having deflection, and after that, because in our entire test section we are not having now gradient of the density, so after that it will be actually moving in single direction. Okay, so it means for the light wave to deflect we should have the gradient in refractive index, or in other words I should say the gradient of change of density. Okay, so what particularly will be happening, now we can take one typical situation, that if inside our test section I consider situation of a compressible supersonic flow. So in case of compressible supersonic flow, we will be having the occurrence of the shock wave. Okay, so I can consider that in my test section, say this particular location is nothing but corresponding to the occurrence of a shock wave. Okay, so what I am now considering, that above this I am having high density, and below this I have some low density, and at this particular junction where we are having the occurrence of the shock wave, at this particular junction what will be happening, we will be having nothing but sudden change of density value, so we will be having the gradient of density field. Now I may consider that a large number of rays we have actually incident on this particular test section. So what will be happening over here, the rays which are actually passing through the constant density section. So over here you can see in this particular zone above the shock wave we are not having any gradient of the density, so these rays will be actually directly moving along a straight path. Okay, so these will be actually move in the direction along which these are actually incidented. Okay, and what will be happening, particularly the rays which will be actually passing through this shock wave, these will be having certain reflection, deflection. Okay, so because of that their angle will be actually changing from the angle of the incident. Okay, so over here you can see that if I consider this is say my some screen over which this light is actually falling. Okay, so I can now consider the two different situation. In first situation I may consider that if I don't have any fluctuation of the density within our test section, corresponding to that I'll be having nothing but constant intensity of light. So this is my say I1 as constant intensity when we are not having any no density gradient. Okay, so when we are having not having any density gradient. So in that particular case, what will be happening? We will be finding nothing but everywhere we will be having the same intensity of light on our visualization screen. Okay. However, what will be happening when we are having this particular type of situation, then we will be finding that in some of the zone, we will be having actually very bright contrast, and in particularly the portion which is directly in front of this occurrence of the shock wave, we will be having nothing but a dark zone. Okay, because whatever the light wave was moving along that path, that has actually not taken that direction and it has deflected to some another. Okay, so because of that what will be happening in some section, so this was my intensity when I was actually considering that we are not having any density gradient. Now if I draw the profile of the density corresponding to this particular situation which I have shown over here, so in that case what will be happening, we will be having nothing but in this bottom zone we will be having a constant intensity whatever was there earlier, and now at this particular point, say if I consider this as nothing but my location corresponding to the shock wave. So what will be happening at this particular location, we will be having actually a dip in the intensity of the light. Okay, and whatever the dip we are having in the intensity, that dip we will be actually getting the compensation in terms of high intensity value at the point where actually this wave is actually joining. So if I consider that this wave is joining near the corner, then we will be having particularly at this corner location high value of intensity. Okay, so this you can see over here that now corresponding to the new intensity profile, basically we are having the total intensity of the whole image has remained same. However, at some particular location we are getting very high intensity, and wherever we are having the occurrence of shock wave corresponding to that, we are getting nothing but a dark spot on our screen. Okay, so it means you can see the point where we are having nothing but occurrence of the shock wave, or I can say where we are having the occurrence of the gradient of density field. Corresponding to that, we are getting nothing but a dark spot. Okay, so as I have already told you that we will be having nothing but this deflection in the incident light wave. So we can either measure this angle, or in some of the measurement techniques we can employ the measurement of this deflection distance. So this displacement what has actually taken place. Okay, now one important point, as I have told you, that we may have shift of phase also while we are having actually the situation of density gradient. So that also let us try to see. Okay, so now what I am considering that in this test section, say at this particular location, corresponding to this particular location, my refractive index is nothing but n, and now I have taken some location at distance dy above. So let me consider this as my point A, and another location at distance dy below my this mean position, and let us consider this is as nothing but my point B. Okay, so if I consider that my gradient of refractive index is nothing but del eta by del y. Okay, so now what I can do, I can specify that refractive index at point A will be nothing but eta plus or I should say it n. I am calling refractive index as n. So NA will be nothing but n plus del n by del y into dy, and NB will be nothing but equal to n minus del n by del y into dy. So these will be my corresponding refractive index values. Okay. Now we know from our fundamental definition of the refractive index that refractive index is nothing but equal to C naught by C, where C is nothing but speed of sound in speed of light in vacuum, and this C is actually speed of light in our medium. Okay, so from this I can say that my eta is nothing but inversely proportional to the speed. Okay, so if I consider that I have some light wave which is actually starting at this particular point A, so I can write that its velocity is nothing but VA, and a light wave which is starting at this point, its velocity let me write as VB, and corresponding to this central location, if I have any light wave, let us consider that its velocity is nothing but V. Okay, so now I can write VA as nothing but V times, because it is proportional to refractive index, so V times n divided by NA, where NA is nothing but n plus del n by del y into dy. Similarly, I can write value of this velocity of the light ray corresponding to location B as nothing but V times n divided by n minus del n by del y into dy. Okay, so it means you can see over here this particular value in the denominator corresponding to VB is actually less, and this value is more. So I can clearly say that my velocity of beam B will be greater in comparison to the velocity corresponding to light ray A. Okay. So generally, while we are having the propagation of the light, it will be nothing but having in the form of electromagnetic waves, and we will be having some maximum amplitude locations and minimum amplitude locations. Okay. So now what I can say that if I have considered that two light waves have started at the same point, and if I try to trace the location of their maximum amplitude, okay, so what will be happening? We will be having actually, and I am considering that the wavelength of both these lights rays is actually same. So in that case, what will be happening? I'll be finding that if I have the gradient of refractive index, or I should say, in other words, the gradient of density inside this field. So what will be happening? This particular, if I trace the location of uh, maximum crest location after some time delta t, so say corresponding to this beam A, I am getting the location at this particular point. Now corresponding to the ray B, I'll be having obviously some faster travel. Okay, so because of that, what we'll be having? We will be having nothing but phase shift in between our ray A and ray 2. So we can also employ some techniques based on the measurement of change in phase shift, and that also can be actually employed to visualize our flow field. Okay, so this is the whole idea of using the density based flow visualization techniques. Basically what is happening, density is changing the value of the refractive index, which is changing the path of the light travel. Okay, so based on that, actually we are trying to visualize this uh, different patterns, intensity patterns of the light rays on our screen, and based on that we are trying to visualize the flow field. Okay, so this is one typical representation which I have shown over here. So in this, I have shown that this deflected ray is making some angle epsilon with the direction of the incident ray. So over here, you will be finding that this epsilon is nothing but lambda divided by n1 into d eta by dy. Because while this ray will be only deflecting if we are having the change of gradient in the normal direction. Okay, so d eta dn by dy I have taken, and this I have taken corresponding to location y equal to y1. Now we already know from our equation that n minus 1 is nothing but equal to k times rho. So from this I can relate that my dn by dy will be nothing but equal to k times d rho by dy, and k is some constant which I can simply write as 1 by rho s, where this rho s is nothing but specifically termed as the standard density of the medium at standard conditions. Okay, and this lambda is actually replaced by L into beta, where this beta is also some constant. Okay, and the value of this particular constant depends upon the gaseous medium whatever we are considering. Particularly for air, the value of this constant is nothing but equal to 0.000292. Okay, so over here we can see that whatever the angle of deflection we are having, that is nothing but proportional to the gradient of density. So it means if in any of the measurement technique we are measuring the angle of deflection, that is nothing but giving us the gradient of the density field. Okay, now we also have one parameter eta. So eta is nothing but refers to the refractive index of this particular medium. So you can see eta is nothing but 1 plus beta times rho by rho s, and this outside we are having n1. Okay, and over here also we are having n1. So this n1 is nothing but refers to as the refractive index of surrounding medium, whatever the medium we are having outside our test section. Generally what we do, we take the value of this eta 1 as equal to 1. Okay, so this is the whole idea of using the density based flow visualization. Okay, now let us try to see that what are the different methods available. So we are having shadowgraph, where we will be nothing but directly taking the photograph or image on a screen. Okay, and in this particular shadowgraph, what we do, we measure the value of displacement delta. Okay, Now, from this previous diagram, you can see over here this angle of deflection is nothing but epsilon, and the corresponding displacement on the screen is nothing but our delta. Okay, so now you can clearly relate the value of this delta along by considering the distance, this particular distance y of the screen. So corresponding to that, you will be finding while we are measuring delta, it is nothing but proportional to delta is nothing but proportional to del epsilon by dy. Okay, so because of that, what will be happening? Because we are already knowing that epsilon is proportional to del rho by del y, so we will be nothing but getting whatever the sensitive parameter we will be getting, that will be nothing but reflecting the uh, derivative of gradient of the density field. Okay, so that's why while we are measuring the displacement corresponding to that, we are getting nothing but the corresponding double derivative of the density field. Okay, then we have another technique, slurring or Moir deflectometry. So in this particular case, we will be having measurement of deflection. So that's why I will be getting nothing but the gradient of the density field. Then the techniques where particularly the interferometry, where we will be measuring the phase difference. In that case, in some situation we will be getting the gradient of the density field, and in some cases what we do, we try to compensate the phase shift. So for these techniques, we can use some additional arrangement in order to even obtain the directly the variation of the density field. Okay. In terms of complications, if we see, so shadowgraph is actually very easy technique. Then we are having a moderate level of difficulty associated with the slurring technique, and particularly the interferometry techniques are actually involving very complex systems. Okay. Now, in case of shadowgraph, what we do, we nothing but allow the light to incident on our test section. And as I have already told you that within our test section, if I consider that at this particular location I have the change of the or the gradient of the density field, then what will be happening? Light at other locations will be actually moving along the straight path, and particularly at this corresponding location, it will be actually deflecting at certain angle. Okay, so because of this deflection of the light, what we will be getting on our screen, we will be finding that at some point we will be having higher intensity, and corresponding to the point where we are having gradient of the density, we will be having actually a dark spot. Okay, so that is something which we will be getting. So now instead of seeing this light on a screen, what I can do, I can have another lens, and then I can record this with the help of some camera. Okay, so the typical photographs which are taken using this shadowgraphy are shown over here. So in this first photograph, you can see this is nothing but shows the flow of air over a heated cylinder. So this white spot over here is nothing but a heated cylinder, and over this heated cylinder we are having the flow of air, and obviously because air will be rising because of the buoyancy effect, so we will be having nothing but so wherever we are having the density change of density field corresponding to that, we are getting the dark spot, and in other locations we are having nothing but higher intensity over the image. Okay, then this particular photograph is actually corresponding to the motion of a bullet. So you can see the motion of the bullet is actually uh, recorded using this shadowgraphy. So particularly this particular dark spot, which you can see over here, this particular dark spot is actually corresponding to the shock wave, occurrence of shock wave. So we will be having sharp change of density corresponding to this shock wave, and after the shock wave we will be having you can see these small patches also are coming. So these small patches are coming because of the occurrence of the expansion wave. So what happens actually behind the shock wave, we will be having some points where we will be having small changes in the density field. So corresponding to that, whatever the waves we are having, we call these as expansion waves. So these small spots, whatever we could infer, these are nothing but represents the occurrence of the expansion wave. Then we have one more situation where flow is taking place over a wedge structure, and across the wedge you can see this is a dark spot which is coming over here. So this dark spot, once again, nothing but recording the occurrence of the shock wave. Okay, so these type of photographs where we are having the changes in the intensity pattern, that particular photograph is something which is known as a shadowgraph. Okay, and the methodology employed or the technique employed is known as shadowgraphy. Then another method we are having is slurring technique. So in this particular slurring methodology, what we do, we are having light source. Then once again, we are having a lens which will be converging the light in a particular direction. Now, let me consider that I have the change of density field at this particular location. Okay, so because of that, what will be happening at all other locations, we will be having light waves which will be moving in the direction of the incident ray. However, corresponding to this particular location, we will be having nothing but deflection in the path of the light wave. Okay, so now over here we are having one more lens. So this particular lens, what will be what it will be doing? It will be actually focusing once again the light to a point. So what will be happening? Whatever the incident waves were coming or rays were coming, which were not changing the path, these will be actually focusing at this particular location, and whatever the ray which has deflected, that will be having actually the focal point at some another length. Okay, so now we can do employ two methods. One thing we can do is we can actually just use some sharp knife edge like structure in order to remove the intensity of the light which is actually coming undeflected. Okay, so in that case, what will be happening? Our camera lens will be only taking the light ray which has actually deflected, and because of that, while we will be recording the photograph on our screen, we will be finding that we will be having a sharp intensity point corresponding to that of the object where we are having change of density field, and apart from that we will be having nothing but dark spot. Okay, and in the second type of situation we can also do that we will be actually stopping the path of this particular deflected wave. So in that case, we will be getting nothing but dark spot corresponding to our object. Okay. So now what will be happening? Now depending upon, so generally what we do, we actually try to block the path of the beam only which has come actually undeflected. Okay. So in this particular arrangement, what we can do, we can actually find out that how much change in intensity will be there corresponding to the original intensity of the image when we are not having any obstruction in our flow field or any gradient of density in our flow field. So this particular point you can see over here. So this is nothing but A dash and B dash I am considering as my total beam of light which has actually come through this particular spot. And now what we have done, we have placed a knife edge obstruction, and this obstruction is placed in such a fashion so that it is allowing only the light wave to move through this section through this linear distance y1. Okay, so if this is our entire beam, we are obstructing some portion of the beam and we are allowing y1 portion to actually pass through it. Okay, so now what will be happening if we are having say delta y as nothing but this small deflected portion of the beam. So obviously this small deflected portion of the beam, if I consider this as my lens 2, so this will be having some focal length f2. Okay, so corresponding to this deflected ray, I'll be getting the linear change over here at this particular location as nothing but equal to f2 times epsilon. Okay, so if now I try to find out that how much contrast we are having in our image, that will be nothing but equal to delta I, so change in intensity corresponding to that of the original intensity. Okay, so the original intensity is something which is actually going through this linear distance y1, and delta y is the displacement corresponding to the deflection epsilon. So because of that, we will be having this change in intensity proportional to our delta y, and original intensity will be proportional to y1. Okay, so this delta y I can now write as nothing but f2 times epsilon divided by y1. So from here I'll be getting that now this epsilon, I have already seen the formulation of epsilon in terms of density gradient. So if I just substitute that over here, I'll be finding that C as nothing but equal to F2 times L beta divided by Y1 rho S into D rho by dy. Okay, so that is something which will be showing us nothing but the contrast of light on our final photograph which we will be obtaining. So it means based on this contrast of light, we can nothing but relate it directly to the gradient of the density field. Okay. So you can see over here, these are the photographs which are recorded using this slurring technique. So in this first case, we are having nothing but a electrical solder iron. So from this is a nothing but hot solder iron. So from there, what will be happening in the surrounding, we will be having natural convection. So whatever the air will be coming in contact with this iron rod, that air will be actually rising in upward direction, and its density will be decreasing. So this particular portion you can see over here nothing but represent the eddies of this air medium which are actually rising above the hot air which are rising above the soldering iron rod. Okay, then another condition we are having over here, so you can see this is nothing but a spherical ball. So this spherical ball is actually falling inside flow field, particularly at the sonic velocity. So you can see over here this particular contrast over here nothing but shows the different density field which we are actually obtaining in our flow. Okay, so based on the slurring photography, what we will be getting, we will be nothing but getting our gradient of the density field, which will be actually seen in terms of different contrast of the light intensity over our photograph. And another technique we are having as interferometry. So in case of interferometry, we are having a light source which will be passing through this lens L1. Then we are having some splitter S1. So this splitter will be actually equally distributing the light beam into two different paths. So for example, beam 1 we have got in this particular direction and beam 2 we have got in this direction. Then we are having some mirror over here, and this mirror has directed the light now in downward direction. Now, once again, we are having some mirror which will be once again directing this light now along this particular direction. Now, what we are having, where we are having actually the path of beam 1, in that path we have actually placed our flow field. Okay, so what will be happening inside this flow field, if we are having the gradient of the density field, because of that we will be having nothing but change in phase of this light ray. So because of that, what we will be finding over here at this particular splitter section, once again we are joining this beam 1 and beam 2, and then we are focusing this on this lens L. Okay, so now what will be happening in this particular in the path of this beam 2, we are not having any obstructions over here. However, over here what will be happening and because of the flow obstruction, the distance traveled by this beam 1 will be actually different than the distance traveled by this beam 2. So because of that, what will be happening, ultimately we will be finding some phase shift at this particular joining position, and depending upon the shift of the phase, we will be having occurrence of dark and bright spots. Okay, so for example, you can see over here, if I consider that my beam 1 is coming like this, and if my beam 2 is also having same phase to that of the beam 1, so in that case what will be happening, we will be having our final output light wave as nothing but of amplified magnitude. Okay, so we will be getting the brightest spot corresponding to this particular situation. And if I have a situation where say this is my beam 1, okay, and I have some phase lag in between our beam 1 and beam 2, and let us consider if that phase lag is nothing but equal to 180 degree. In that case, what will be happening, my final wave, whatever I will be getting, that will be nothing but, this is nothing but my plus amplitude, this is my negative amplitude. So while we will be doing the summation at this particular junction, we will be getting nothing but as our dark spot. Okay, now depending upon the optical length which is actually increased or decreased by the presence of this flow field, we may have phase lag at any value in between 0 to 180 degree. So corresponding to that, we will be nothing but getting our final light beam, and depending upon the superposition of the two light beams, we will be having the intensity pattern corresponding to that. Okay, so over here we are saying that if our beam is actually traveling, beam 1 is traveling delta L extra distance because of the presence of the flow field, so that delta L extra distance will be nothing but L times n minus n naught, where n naught we are considering the refractive index of this surrounding medium, and n we are considering the refractive index of this flow field, whatever we are having. Okay, so this delta L, because we are having the direct dependence in between n and density, so this I can write in terms of the change in density field as beta times L rho minus rho naught by rho s. Okay, so now if we have to find out that how many number of fringes we will be getting, that will be nothing but equal to delta L times divided by the wavelength of the light beam. So that will be representing us the number of fringes which we will be getting. Okay. Now, depending upon the situation, whether we are having zero phase difference or we are having 180-degree phase difference, we will be getting highest and highest image intensity. So corresponding to that, I will be having nothing but the brightest fringe pattern, and corresponding to that, I will be having darkest spot. Okay, on our screen. So corresponding photographs which are obtained using interferometry, you can see over here. So here we are nothing but having array of 3 cylinders. So these are the heated cylinders over which our flow of air is taking place. So obviously, while the air will be rising in upward direction, we will be having gradient of the density field in this upward direction. So you can see we are getting some fringe pattern. So this particular fringe is nothing but corresponding to the constant density value. So for each value of density field, we will be getting a fringe. Okay, so we will be having the sequence of fringes of dark and bright portions. Then the corresponding profile of air is there over an electric bulb. Then this particular profile of air is actually exactly drawn on the surface of this bulb. Okay, so what we are doing actually, based on the gradient of the density, nothing but we are trying to image our flow field over here. Okay, then another method which can be employed for flow visualization, it's nothing but a very simple method. So in this particular method, what we can do, we can inject smoke particles into our flow field, and now what will be happening, these smoke particles will be actually traveling into our flow field, and now we can record the path of these smoke particles, and based on that also we can actually try to visualize our flow field. However, in this particular smoke method, we may have one disadvantage, that we may have certain spots close to the wall or in some other locations where our flow, our smoke particles will not be able to reach. So because of that, we will not be able to resolve the intricate flow fields. Okay. So this is all about the flow visualization based on the gradient of density field. Now I will try to discuss over here some of the very basic flow measurement devices which are known as positive displacement based flow measurement. So the very first device which I have included over here is nothing but a nutating disk meter. So you can see over here that we are having some disk body, and inside that we are having some spherical ball like structure, and over this spherical ball we are having one disk which is connected to this ball. Okay, so now what is basically happening, this disk is having, I have included one animation over here. So in this animation you can see that this disk is actually having some nutating motion over here. So while this disk is nutating, it is actually allowing some fluid medium. So you can see over here, this fluid medium is actually entering at this particular location, and then because of the motion of this disk, it is opening this outlet, and because of that, some this liquid is actually moving in the outward direction. Okay, so nothing but over here, what we are having some fixed volume of this our casing. Okay, so in this particular fixed volume, what will be happening in half of the cycle of this disk motion, we will be having inflow of the liquid, and in half of the cycle we will be having discharge of the liquid to our outflow. Okay, so for example, in this particular photograph, you can see while this disc will be rising in upward direction, during that time we will be having filling of this chamber, and while this disc will be moving in downward direction, during that time we will be having outflow over here from this particular location. Okay, so it means now if we consider that how many times this disk has moved in upward and downward direction, depending upon that we will be having actually we can determine, because we are having the fixed volume of this cavity, so we can relate that upward and downward motion of the this disk with the number of times it has actually number of times it has moved in that particular motion. So based on that we can try to find out the flow rate. So this particular type meter is employed for measurement of low liquid flow rates. Okay, so it is employed for measurement of liquid flow rates, and generally it is employed for measurement of low liquid flow rates. Okay, so here we are having some mechanical arrangement which will be actually moving the spindle of the counter, and based on the rotation of this counter we will be actually getting the corresponding value of the flow rate. Okay, so this type of meter are normally employed in our home applications also for measuring the amount of water. Okay, this type of meters gives us both the flow rate value as well as the cumulative value of the liquid which has passed in a certain period of time. Then another type of positive displacement method may be rotary vane like flow meter. So over here what we are having nothing but some eccentric casing, and then we are having a rotary drum over here, and in this particular rotary drum we are having some vanes over here, and inside this we are having nothing but some springs attached. So basically what will be happening while this rotor will be rotating, these vanes will be always in contact with the casing. Okay, so for that purpose we are having some springs over here. So while the flow will be coming from this inlet section, it will be moving through this particular section to the outlet. So depending upon the rotation of this eccentric drum, we can actually relate directly to the flow rate. So in this particular type of arrangement, we will be having nothing but the continuous flow of the medium. Then another type of arrangement, positive displacement method, we may employ is actually lobed impeller flow meter. So over here you are having we are having some lobe structures, and these lobes will be actually moving, and while these will be moving, these will be actually covering certain fixed volume, and depending upon the number of rotations of the lobe we can determine the flow rate. Okay, so this type of positive displacement devices are actually required for measurement of the flow, where we have to go for very accurate measurement. Okay, because positive, in case of positive displacement devices, what will be happening in each revolution of this mechanical arrangement, we will be having fixed discharge. Okay, so discharge will not be varying over here. So that's why these methods are actually very accurate methods for the measurement of the